The Sun. The heart of our solar system is a yellow dwarf star, a hot ball of glowing gases. Its gravity holds the solar system together. Electric currents in the Sun generate a magnetic field that is carried out through the solar system by the solar wind, a stream of electrically charged gas blowing outward from the Sun in all directions. The connections and interactions between the Sun and Earth drive space weather conditions on our planet, which can affect satellites and power grids, change the radiation belts, and trigger the aurora. And never before have we been able to study it so closely. NASA's Parker Solar Probe is diving into the Sun's atmosphere, facing brutal heat and radiation, on a mission to touch the Sun. And this spacecraft is changing the way we see and understand our nearest star. Today, NASA will reveal the surprising discoveries that this unprecedented spacecraft is uncovering about our Sun.
Hello, and welcome to NASA Science Live. This is an opportunity for you to come behind the scenes and get to know your space agency. I'm your host, Gray Hautaloma. This show is all about you being able to interact with NASA scientists and to get your questions answered. Visit us on Facebook or Twitter and ask us a question using the hashtag AskNASA, or leave a question in the comment box wherever you're watching this. Today we're taking you on a journey to touch the Sun with NASA's Parker Solar Probe. Parker is traveling through the Sun's atmosphere closer to the surface than any spacecraft before it. It faces brutal heat and radiation conditions, and it's giving us the closest observations of a star that we've ever seen. Today, we're going to share with you some of the first results from that amazing mission and explore the ways it's helping us understand our star in new ways. But before we get into the details, let's learn a little bit more about the basics of sun science.
The wind speed of a devastating Category 5 hurricane can top over 150 miles per hour, or 241 kilometers per hour. Now imagine another kind of wind with an average speed of 0.87 million miles per hour, or 1.4 million kilometers per hour. Welcome to the wind that begins in our Sun and doesn't stop until after it reaches the edge of the heliosphere, the solar wind. The corona is the Sun's inner atmosphere, the brightness that can be seen surrounding an eclipsed Sun, and home to the continually expanding solar wind. Right now, the Parker Solar Probe, a NASA mission launched in 2018, is orbiting the Sun and will get as close as 3.83 million miles, or 6.16 million kilometers, of the Sun's surface. Parker is gathering new data about the solar particles and magnetic fields that comprise the solar wind. More specifically, two of its main goals are to examine the energy that heats the corona and speeds up the solar wind, and determine the structure of the wind's magnetic fields. While many theories describe the solar wind's history, this is what we do know. The solar wind impacting Earth's magnetosphere is responsible for triggering those majestic auroras, typically seen at locations close to our north and south poles. In some cases, it can also set off space weather storms that disrupt everything from our satellites in space, to ship communications on our oceans, to power grids on land. Knowing more about the effects of the solar wind is not only important to those of us who live on Earth, it will be critical to know how to mitigate its effects once our astronauts travel back to the Moon and beyond for extended periods of time. My feeling is, if the Sun sneezes, Earth catches a cold, because we always feel the impact of what happens on the Sun thanks to the solar wind.
Well, as you saw, the Sun is very active, and all this activity influences the Earth and our entire solar system. We're 93 million miles away, and there's only so much we can see from this vantage point. But thanks to NASA's Parker Solar Probe, we're learning a lot more about our Sun up close, things you can't see from Earth. I'm joined today by Parker project scientist at the Applied Physics Laboratory in Laurel, Maryland, Noura Wafi, and Dr. Nikki Fox, head of the Heliophysics Division at NASA headquarters. So we've talked a little bit about the basics of the Sun through that video, and we're going to learn a lot more about Parker science and the great things that we're learning from it. But let's talk about a little bit about the basics. Nikki, if you could just start by, what is the Sun made of? Talk about the composition of it.
So the Sun, I like to think of it as the Sun is made of everything that you're made of. So the Sun is when it had the Big Bang, it threw out everything that actually constructed our solar system and the very fabric of life. And so we're really almost all made of stardust. The sun is predominantly hydrogen. There is helium and some other heavier ions in there. And the sun is very important to us because, of course, it's a star. And so not only are we studying the sun and finding out why it's so important to us here on Earth, but we're also for the first time really going into the atmosphere of our star.
So the sun is a glowing ball of hot gas. This gas is so hot. It's hot to the point where atoms split in negatively charged electrons and positively charged ions. And this makes what we call a plasma. And plasma, usually there is currents in it, and these currents create magnetic fields. So the sun has a hot plasma that is magnetized at the same time. And the magnetic field plays a key role in all the processes that are occurring in all the layers of the solar atmosphere. And going back to what Nikki said, 75% of the mass of the sun is protons and hydrogen, basically. The rest of it is helium. But there are traces of heavy ions, heavy elements like oxygen, carbon, iron, and others.
So the atmosphere of the sun, it is made up of all those too. Tell me about how that all relates. We think of planetary atmospheres, but what is the sun's atmosphere?
That beautiful atmosphere around the sun, we call it the corona, and of course a lot of us were really treated to an amazing show back in 2017 when we had that wonderful eclipse across America. And that's the only time that we're actually able to see the corona without using special telescopes that we build. And so that corona, it's very mysterious. It is really made of the sun's atmosphere. It is basically everything coming off the sun and being sort of held in that region around the sun. And it is one of the mysteries for us is it's actually 300 times hotter than the surface of the sun, which is just something that we need to go and study.
So there are other mysteries. Let me go back to the solar eclipse. It's really an excellent example. If you look at different solar eclipses, they look all different. Because the sun is a star, it's magnetizing, active, and it's always changing. And as such, there is so many processes that are going on that create phenomenon like the coronal heating that you talked about. But there are other ones like the breeze of protons and electrons that is continuously leaving the sun to bathe Earth and the rest of the solar system that we call the solar wind. The solar wind is accelerated to speeds ranging from 200 to 500 miles per second. And we wonder for decades, where do they get that energy from? And that's a mystery that Parker Solar Probe hopefully will help us to solve.
I know we're going to talk a lot more about the solar wind today with Parker, but tell me a little bit more about the solar wind and like what it is and how it affects the Earth and what we know about it.
So the solar wind is really very key for us. We live in the atmosphere of the sun, and so you see the corona, I mean, it's big, but it doesn't look that big when you see it during a solar eclipse. But that atmosphere is actually streaming all the way out. It bathes all of our planets on the way to the very edge of our solar system. In fact, it shapes our very place in space. So it kind of creates almost like a windsock around the whole solar system as it is orbiting around the Milky Way. And so it's really shaping it. It's the sun goes right the way to the very edge, and it interacts with interstellar space and really shields us from all of the nasty stuff that's in interstellar space. So that the solar wind is really protecting us. Now, also in the solar wind, all these particles continually streaming towards us, as Noor said, that they carry a magnetic field with them. The Earth has a magnetic field too. And so sometimes these things can interact and allow just huge amounts of energy to come into our magnetic atmosphere, our magnetosphere, causing big churning and big activity that we call space weather. And so it has a profound impact for our astronauts and also all of our technology that we rely on every day.
And that's actually why why understanding the corona is not an option for us. We need to understand it. And we have been studying the corona for years and years and years, for decades. And there are still these mysteries that we are struggling with. And the best way to prevent the devastating effects of space weather is to prevent it. And by prevent it, we have to predict this phenomenon like coronal mass ejections, like flares. And we need that basic understanding of how the solar corona works first in order to go to the second step and to predict this phenomenon.
Yeah, I think you've kind of gone over it. I guess do you have anything more to say about why it's important to understand the sun? It's very fascinating. We know a lot about it already. Why do we need to keep studying it?
So we've looked at the sun in just about every wavelength possible, and we have sent spacecraft all the way in as far as the orbit of the planet Mercury. But we've never been able to go right into this heart, this source region. And so it's like, you know, you want to understand how a waterfall is formed. If you're at the bottom of the waterfall, you have no idea what's up there actually causing it. With Parker Solar Probe, not only are we going up the waterfall, but we're going all the way down the river to the very source, that tiny little trickle, to be able to now, for the very first time, go into that source region where all of this interesting physics is happening, where the coronal heating is happening, and where that acceleration of the solar wind. And so it is very critical that we go into this region because it's the first time that we can really get the data we need. As Noor said, we've waited decades and decades for this information. So that's why we're so excited to be here today.
All right, well, thank you so much. And we're going to talk a lot more about these things as we go through this. But we just learned, we've learned some of the fundamental science happening at our star. And why don't we hear right now from some of the leaders of this mission about what they found out in these first 4 papers that are coming out today in Nature. Let's hear from them right now.
50 years after the beginning of space exploration, we still don't understand what's heating the solar corona, accelerating the solar wind up to really high speeds.
So there's this long-standing mystery: how do you create a hot corona from a cold star?
And by going in very, very close to the sun, we're learning about the sources of energetic particles, where they begin, right down in the solar atmosphere or corona.
Well, the solar corona is the upper atmosphere of the sun. That's millions of degrees. It's very hot. Whereas the photosphere, the white light sun that you see in the sky, is cool. And so the idea of Solar Probe is to actually go there into the corona and make the measurements that are behind the plasma physics phenomena.
The Parker Solar Probe is getting so close to the sun that it will answer questions that we can't even formulate right now.
My hope is that with Solar Probe, we're finally going to get close enough to the sun we can directly measure the solar wind in the corona.
If you're trying to study the source of a waterfall, understand the origins of a waterfall, but you're at the bottom of it and all you see is this mixed up turbulent mess, it's really hard to understand what's happening at the top of the waterfall. And that's what we're doing now. We're getting closer and closer to the top. I think we're on the cusp of being able to answer the question of what heats the solar wind.
Figure out what physics is actually responsible for these high temperatures and the acceleration of the wind to these supersonic speeds.
WSPR has already seen some things that are giving us hints into some of the long-standing predictions of what we might see.
The instrument is working really well, and the results are